Undefined behavior is a concept that every programmer must grasp, especially those who work with lower-level languages like Zig. When we say something is undefined, we mean that the value can be anything, even something nonsensical according to its expected type. This can have significant implications for performance, debugging, and the overall behavior of your programs. Today, we're going to unravel the mysteries of undefined behavior, explore its causes, illustrate with code examples, and discuss how to avoid pitfalls in your coding journey. Now let's take a look at how we can implement a simple division function in Zig that showcases the concept of undefined behavior. In this example, we define a function called divide that takes two integer parameters, x and y. The fundamental operation here is dividing x by y. However, a critical element to note is the check for division by 0. If y equals 0, we don't perform the division. Rather, we return 0 arbitrarily, which should ideally trigger a runtime error. This highlights a potential pitfall in error handling. Returning a fixed value in an erroneous situation might lead to confusion and undefined behavior later in the program. Next, we call this divide function with arguments 10 and 0. This deliberate choice of a 0 divisor leads us directly into the context of undefined behavior, as operations involving 0 and division must be handled with care. Understanding what happens at runtime is crucial, as different environments or compilers might react differently. Some could throw an error, while others might yield unpredictable results. This simple illustration emerges as a powerful reminder of the importance of robust error handling in programming to ensure the reliability of our applications. Now let's take a look at an example that demonstrates how accessing out-of-bounds elements in an array can result in undefined behavior. In this code, we start by importing the standard library in Zig, which gives us access to useful functions for debugging and other utilities. We declare an array, R, with a specified size of 3 elements containing the integers 1, 2, and 3. However, the line that follows attempts to access R3, which is beyond the bounds of the declared array. While the array is indexed from 0 to 2, attempting to access the fourth element, index 3, is a violation of the array's defined limits and results in trying to read data from an area that hasn't been allocated for our array. Fortunately, Zig incorporates runtime safety checks that will identify this out-of-bounds access. When this code is executed, Zig will catch this mistake and throw an error, preventing the program from crashing or behaving unpredictably. This highlights the critical need for safe indexing practices and careful array management to avoid the pitfalls of undefined behavior in programming. Now let's take a look at a function that exemplifies the risks associated with uninitialized variables in Zig. In this function, we declare a variable named uninitialized variable of type i32, but we do not assign it an initial value. This means that when we attempt to return this variable, we risk retrieving an unpredictable value, as it holds whatever data happened to be in that memory location at the time. Such behavior can lead to severe bugs, particularly in more complex programs where the output of this function might influence other operations or logic. It's crucial to understand that utilizing uninitialized variables is a common pitfall leading to undefined behavior, where the program behaves unexpectedly. In this example, we subsequently call our function within the std debug print statement to display the returned value. Since we have not guaranteed that uninitialized variable contains a valid predetermined state, the output will be indeterminate. This reinforces the importance of always initializing your variables, as it ensures they start from a known state, thus contributing to safe and reliable code execution. Now let's take a look at how type casting can lead to unexpected results in Zig. In this example, we start by declaring a variable num with a value of 300, which is of type i32. When we cast this integer to u8, we use the Zig function at int to int, which allows type conversion between integers of different sizes. However, it's crucial to remember that u8 has a maximum value of 255. This means that when we convert our variable num, the value exceeds the limit of u8 and will wrap around. The resulting value from this cast will not be the expected 300. Instead, it will yield a value of 44 due to this overflow. Such behavior illustrates the importance of understanding type ranges and the implications of improper casting. Following this, we print the result to the console. While seemingly innocuous, this incorrect casting can lead to serious logical errors in programs where numeric comparisons are made. Hence, it is vital to handle types carefully and ensure that we are always aware of their possible values to avoid undefined behavior in our applications. Now let's see how we can implement a scenario that demonstrates race conditions in concurrent programming using Zig. In this example, the function concurrent_access initializes a shared variable shared value to 0. The crucial part of this code is the spawning of two threads, thread 1 and thread 2, both of which are set to access and modify shared value. When both threads operate on the variable simultaneously, the operation shared value plus equals 1 becomes susceptible to a race condition. This means that if one thread updates shared value while the other is reading it, the outcome can lead to inconsistent or unexpected results. For instance, if both threads increment the value of shared value at the same time, there's no guarantee that the final value will accurately reflect both increments. It might only register one. To mitigate this issue, implementing synchronization mechanisms such as locks is essential. By controlling access to shared value, we can prevent the unpredictable behavior caused by simultaneous modifications. It's important to remember that concurrent programming requires careful handling of shared resources to ensure data integrity. The implications of undefined behavior stretch far and wide. Understanding the concept ensures better programming practices and safer code. But what's the takeaway? One of the key defenses against undefined behavior is thorough testing and the use of tools designed to catch potential pitfalls early in the development process. Zig provides features aimed at promoting safe programming. For example, compile-time safety checks can give you valuable information before you even execute your code. When you routinely perform checks and leverage Zig's safety features, you can mitigate undefined behavior risks. Here's a reminder tip. When coding, always consider what potential pitfalls exist and how to handle them appropriately. Whether it's by checking bounds, managing types properly, or ensuring thread safety, you build a more robust application. In conclusion, undefined behavior might seem intimidating at first, but grasping its principles is essential for writing high-quality, maintainable code in Zig. With clear awareness of the examples we discussed, you can navigate around these pitfalls. Keep in mind that safe coding practices not only lead to effective applications, but also save you from running into frustrating bugs down the line. As our programming journey continues, remember that every potential issue is just another opportunity for growth and learning in code mastery. Thank you for joining me today. Happy coding!